and the front end will kind of transform that computer program into an equivalent model that's amenable to probabilistic checking, like a R1CS or circuit satisfiability problem, and then we'll apply some kind of backend, some kind of SNARK on the circuit or R1CS instance. So this talk is about the backends. And yeah, the end of the last discussion brought up this notion of polynomial IOPs, which is kind of just a general design paradigm for designing SNARKs. So this is in turn, focusing just on the back end. This is like a three-step process for designing a SNARK. So first you give what's called a polynomial IOP for R1CS or circuit satisfiability. I'll say more later in the talk of what is a polynomial IOP if you haven't heard of this. And then what you do is you combine that with a cryptographic object called a polynomial commitment scheme that turns your polynomial IOP into a succinct but interactive argument. But it'll be public coin typically. So you can then render the succinct interactive argument non-interactive using the Fiat-Shamir transformation, and then you have a SNARK. So this is the paradigm that I really want to talk about in this presentation. And the sumcheck protocol, which was referenced in the title, is a key technique specifically for step one, for designing very high-speed polynomial IOPs. Okay, so the sumcheck protocol was originally described not in the context of SNARKs, but in the context of interactive proofs. So I'd like to briefly, remind everyone what is an interactive proof. So you can imagine that there's some computationally weak verifier, think your laptop or your cell phone or something, that ships a bunch of data up to a powerful prover like a cloud computing provider, and then asks this prover, this cloud provider, a question about the data, and the cloud uses, its substantial resources to compute the answer, but the user doesn't blindly trust the answer as valid, and instead starts interrogating kind of the cloud, the prover, sends a sequence of challenges, get a sequence of responses in return, and at the end of this interrogation decides whether to accept the answer as valid or reject it as invalid. Okay, so the sumcheck protocol is particularly useful for designing what are called doubly efficient interactive proofs. These are interactive proofs where the verifier runs about as fast as you could possibly hope for. So the verifier essentially just reads the input and doesn't do much extra work on top of that. And then the prover, we insist, should run in polynomial time. Ideally, the prover will just compute the answer and then do a little bit of extra work to prove that the answer is correct. Okay, so I want to spend just a couple minutes giving the technical ideas underlying the sumcheck protocol. Since this is a short talk, I won't go too deeply into the ideas, but I think I can give a good sense of it. So the first thing I want to describe is something probably many of us are familiar with, which is a very efficient randomized method to test whether two low-degree polynomials are equal. Okay, so if we're given as input two polynomials g and h, they're both low degree, and we want to know, are they the same polynomial? So what you can do is you can just pick a random input and evaluate both polynomials at that input. And if they agree at that one input, we're going to declare them to be the same polynomial. And of course, if they disagree at that input, we know for a fact that they must not be the same polynomial. And there's this very basic fact to low degree polynomials. Again, this is probably known to most of the audience, that if the polynomials are both low degree and they're not the same polynomial, then when you evaluate them at a random input, they disagree with high probability. And hence this randomized check will kind of be accurate, right? Like if g and h are not the same polynomial, this randomized check will detect that they are in fact not the same polynomial with high probability. Okay, so with that out of the way, I want to describe a highly simplified version of the sumcheck protocol. Despite the fact that this version is so very simple, it's actually remarkably powerful. This has been used to prove some really amazing results. So imagine we want to design an interactive proof computing some function f. Okay, now to apply this highly simplified sumcheck protocol, I need to make two assumptions about f. Okay, the first assumption is that for any input x to f, I'm going to assume that there's some reasonably low degree polynomial that depends on x. I'm going to call it g sub x. Okay, so that evaluating f on x is equivalent to summing up the evaluations of g over a small set. Okay, so this might be a little bit to absorb all at once, but what I'm saying is for any input x to f of x is equal to the sum of this related polynomial g's evaluations, let's say on the integers 1 up to root n. So this is some kind of succinct way of specifying F's evaluation on any input X. Okay, the second assumption I want to make is that anyone can evaluate G sub X very quickly at a single point. Okay, so given X as input, like the verifier sees X as input, given X as input, it might be very hard for the verifier to explicitly compute G sub X, like to compute all of its coefficients or something like that. That might be too much work for the verifier. But what the verifier can do efficiently is evaluate G sub X at just a single randomly chosen point very quickly. Okay, so these are my two assumptions about F. And if these two assumptions hold, then we have the following like really, really simple, doubly efficient protocol to kind of outsource the computation of F to a prover, right? The proof that the prover is going to send is just a polynomial H, which is claimed to equal this polynomial G sub X that the verifier really wants to sum up the evaluations of. Right now, the verifier doesn't trust that H is really as claimed. So what the verifier is going to do is it's just going to probabilistically check that H is as claimed by picking a random input R and evaluating H and G sub X at that random input. I see a question in the chat. The question is why square root? So I want the G sub X to have degree square root n to ensure that the verifier, two things. One is that the proof is short. The polynomial can be specified just with square root n coefficients. And the other reason I want that is so that I can guarantee that the verifier can sum up the evaluations of the polynomial in linear time. So if there aren't many coefficients of the polynomial because it's low degree, you can evaluate it at any point in root n time. Hence, you can compute the sum over root n evaluations in time order n. So that's the protocol. It's complete and sound. The soundness kind of follows the previous slide. That is, if the prover sends a different polynomial than claimed, the verifier's check is going to detect that with high probability. And the verifier is going to run in linear time as desired, because I assume that evaluating G of X at a random point is fast as linear time, and computing the sum of the polynomial, the evaluations of the polynomial sent by the prover is also linear time. So it's like as simple as can be, right? The prover just sends a single univariate polynomial of degree root n. The verifier kind of randomly checks, is it as claimed? And if so, the verifier can efficiently compute the right answer, in linear time. That's it. So it seems so simple, but in fact, if maybe some theorists in the audience might recognize, this is what Aronson, Wigderson, this is exactly what they use to resolve something called the Merlin-Arthur communication complexity of disjointness. It's been used to give doubly efficient protocols for problems like counting triangles and so forth. So it has pros and cons. The pro of this highly simplified protocol is that it's non-interactive. The proof was just a single message specifying one univariate polynomial of degree root n. The big con is that the proof actually gave a complete description of the polynomial. So the proof was kind of long. It was degree root n, it was length root n. When we like to see our SNARKs having proof length like logarithmic or something like that. So it turns out that if the polynomial to be summed were not univariate, but instead were multivariate, then there's an interactive version of this protocol where the proof length is only proportional to the total degree of that polynomial. And that total degree can be much, much smaller than a complete description of the polynomial. So just as an example, I just drew on the slide like a 5-variate polynomial, total degree 3. And I stopped writing terms of the polynomial because I could only fit 10 terms in the slide. But here's a polynomial with 10 coefficients, and its total degree is only 3. So my point I'm trying to make here is that if the proof length is proportional to the total degree of the multivariate polynomial, that can be much, much smaller proofs than simply the prover writing down the entire polynomial and sending it to the verifier. Okay, and that is what the sumcheck protocol of Lund, Fortnite, Karloff, and Nissan does. So it allows the verifier to basically force the prover to sum up all evaluations of a multivariate polynomial, let's say L variables, over all 2 to the L Boolean inputs. So the goal here is to sum up G's evaluations over all 2 to the L Boolean inputs, and the length of the proof will only be proportional to the total degree of G. That can be really, really small. And the number of there's one round for every variable. And from the verifier's perspective, this protocol is essentially a reduction from summing up G's evaluations to evaluating G at a single random point, because the verifier's work is dominated by that task. And there's been a long line of work that has shown that if the polynomial being summed is highly structured in a sense I don't really want to tell you about, then the prover can actually compute all of the messages it has to over the course of this protocol almost as fast as just what's required to solve the problem in the first place. That is to sum up G's evaluations over the Boolean hypercube. Okay, so hopefully that's a reasonable overview of the sumcheck protocol. Now I want to talk about how to use it to design SNARKs. Let me just monitor the chat real fast. Oh, thank you. Yeah, Thaler, for sending the original paper. Okay, so yeah, I guess I have like maybe 6-7 minutes left max. So I just want to give a brief sense of how you can design a SNARK using this protocol. This is taken from a work, it was originally described as a two-prover interactive proof, but like the modern perspective on this work is really that it gave a polynomial IP. So what that is it's a protocol where the prover's first message is a multivariate polynomial H. And so you can think of the prover as like sending H to the verifier, but the verifier doesn't actually get to read all of H. Instead, the verifier is only allowed to evaluate H at a few points. Okay, and after that, the prover and verifier are allowed to execute a standard interactive proof. And once you give a polynomial IP, you can turn it into a SNARK by having the prover instead just commit to H with the polynomial commitment scheme. The verifier gets the evaluations of H using the evaluation procedure of the polynomial commitment scheme. Then they remove any interaction from the subsequent IP part of the protocol using fiat Shamir. Okay, so I think in 2-3 minutes, I can give a sense of how this works. So I'm going to describe it in the context of circuit satisfiability. So the goal here is to determine whether there's a witness W that is an input to the circuit that causes it to output 1. And the polynomial IP makes use of something called a transcript for the circuit. So this is just an assignment of a value to every gate of the circuit that corresponds to like the actual values that those gates take when the circuit is evaluated on a valid witness, right? So if the witness to the circuit is 1030, I kind of filled in the whole transcript on the slide, kind of gate by gate, what value does it take? So that's what a correct transcript is for the circuit. And in the polynomial IP, what we do is the following. So we view each gate as kind of being labeled with a log S bit vector, where S is the size of the circuit. And we view the transcript as a function mapping gate labels to their values. Okay, and the prover's first message in the polynomial IOP is simply a multivariate polynomial, which is claimed to extend, or if you want to encode, a correct transcript. So that is, if you evaluate the polynomial at any gate label, it just spits out the value that the correct transcript assigns to that gate. Okay, so you can think of the transcript itself as like the world's dumbest static NP proof that the circuit is satisfiable, and H as like some kind of encoding of that dumb proof. And the verifier, though, needs to check whether H is actually as claimed, but the challenge is that the verifier can't actually read H in full. It's only allowed to learn a few evaluations of H. Okay, so that's where the sumcheck protocol is going to come in. And the key lemma that lets us use the sumcheck protocol is that the property that the polynomial H extends a correct transcript turns out to be equivalent to checking whether a related polynomial, which I'm calling G sub H on this slide, evaluates to 0 at all Boolean inputs. Okay, and moreover, to evaluate this related polynomial G sub H at a random input, it suffices to evaluate H at only 3 inputs. So, I'm already over my time, I think. So I'm not going to tell you exactly how G sub H is constructed, but I'm just flashing it up on the slide. And you can see to evaluate G sub H at one input ABC, it's enough to evaluate H at the 3 inputs A, B, and C. Okay, so, here's the polynomial IP now. So again, the prover's first message just specifies this polynomial H claimed to extend a correct transcript. We know that H extends a correct transcript if and only if this related polynomial vanishes at all Boolean inputs. Let's imagine for a minute that we're working over the integers. If checking whether G sub H evaluates to 0 at all Boolean inputs is equivalent to checking whether the sum of the squared evaluations of G is 0. right? Because if G sub H evaluates to 0 at all inputs being summed over, then obviously you sum up 0 a whole bunch of times, you get out 0. And working over the integers, if any one of these evaluations is non-zero, then when you sum them up, you sum up a bunch of non-negative numbers, at least one of which is positive, you'll get out something that's strictly positive. So when you work over finite fields, you have to worry about, a bunch of positive numbers adding to 0. You can have wraparound issues, but let's ignore that. That's not so hard to deal with. So that's the polynomial IP. The verifier just applies the sumcheck protocol to compute this big sum. All the verifier has to do in the sumcheck protocol essentially is evaluate the polynomial being summed at a random point. And I said that to do that, it's enough to evaluate H at 3 random points. So that's really it. Like the proof length is logarithmic in the circuit size. The verifier just is runtime is basically dominated by evaluating H at 3 random points. In the resulting SNARK, that's going to come from the polynomial commitment scheme. And we now know how to implement the prover in time linear in the size of the circuit. So just to wrap up, this is the last slide. This is my kind of unified slide. I hope I haven't gone over time. I lost track of how much time I've taken. So Srinath Sethi, sometime later in this workshop, is going to talk about a SNARK called Spartan, which basically it takes the polynomial IP I just described and extends it from circuit sat to R1CS and has some other nice improvements. And there have been some other recent works that just kind of do the same thing, but explore plugging in different polynomial commitment schemes. There's another line of work which is also based on the sumcheck protocol. I guess it has pros and cons compared to what I just described to you. A con is that for deep circuits, the proofs are really big. A pro is that the polynomial commitments are only applied to the witness, not like the whole circuit transcript. So if the witness is small, that can be a nice thing. And then there's a sequence of works that use univariate rather than multivariate polynomials. And a pro of this sequence of works is that their univariate version of the sumcheck protocol is only one round. So if you combine it with a polynomial commitment scheme with constant size proofs of evaluation, you get out constant size SNARK proofs. So you see that kind of performance from systems like Marlin and Planck. However, to get the polynomial commitment schemes to have such small evaluation proofs, they tend to require a trusted setup. They're based on KZG, and that requires a trusted setup. So that's a really nice property of these proof systems based on univariate polynomials, constant size proofs. A con is, concretely, it seems that the prover tends to do some more work. Essentially, they kind of push a lot of the work into the polynomial commitment scheme rather than kind of handling the work in the sumcheck protocol, which can be lower weight. So that is it. I hope I didn't go too far over. Thank you for listening.
Thank you, Justin. We have about 2 minutes for questions. So if someone has like a fairly quick question, then we can squeeze that in.
So the square root of n decomposition that you had in the beginning of the presentation, how does that relate to the normal sumcheck protocol, which uses multivariate polynomials? And how does it relate to Lagrange interpolation? It's not really Lagrange interpolation. I was a bit lost as to where that came from. Is that from an existing work?
Yeah, I guess the short version is, so I stated one con of the simplified version with this root n degree univariate polynomial, which is that the proof is long. It's not polylog. It's root n. It's also just it's more limiting. So this is the big thing. So it takes like a really special problem to be amenable to this simplified non-interactive variant of the sumcheck protocol. So there have been some theory works that have identified some really special but important problems that can be solved in this simplified non-interactive manner. But if you want to do something like give a SNARK for circuit evaluation or R1CS, this very simple non-interactive approach is just kind of not powerful enough to capture what needs to be done. Hopefully that made sense. So I brought it up as a way to kind of convey the main ideas in the multivariate sumcheck protocol, but not to suggest that it's actually a substitute in the applications people the general purpose snarks.
Okay, great. Thank you very much. Do a sort of virtual round of applause.
Thank you.